Good evening, everyone. This is your mentor Rahul Ghosh. Once again, we are meeting for the first time this year. So, a very happy new year to all of you students. Let me quickly check the live session. And today, we are in this session, we are going to cover exclusively aryl halides, right? So, just give me a minute. Okay. Well, I'm unable to find the live program. Anyway, I okay. So assuming that I am already live and you are all able to see me, so I'll quickly move on to the move into the lesson, right? And as we have already maintained that while discussion, if you face any doubt, any question that is in your mind, please feel free to ask me at the given segment, right? You just share your doubts, so I'll be able to help you out from there. Okay, so in first of all, let us discuss their physical properties. If we talk in terms of your dihalobenzenes, then of course we have got the ortho, meta and para isomers, right? Now what we find is that though the boiling point, as far as the boiling point is concerned, it is quite similar of all these three isomers of dihalobenzenes, but if you talk about their melting point, then there is a very large difference between that of the para isomer and ortho isomer, right? You can see here for dichlorobenzene, though the boiling point is very similar, not much of difference, right? Just a 7 Kelvin of difference. However, if you see the boiling point, melting point, ortho isomer is 256 while this is 323, right? So it's quite a difference, almost like 67 Kelvin of difference. So this is exploited to separate the isomers. See, whenever you do halogenation of any halobenzene, so you are obviously going to get an ortho isomer and para isomer, right? Para is always major, that's fine, but how do we segregate them? Since the melting point is extremely, it's quite large, the difference is quite large, therefore by solidifying them we can segregate them, right? So what can be done? They are used to separate ortho and para isomer, right? They are used to separate para isomer from their mixture, right? So this is one property that we will discuss later also, because we need to segregate them in the lab. Here on paper we simply write A and B is formed, but in practically when you are doing this in lab, you need to separate both A and B, right? That is how it goes. Okay, so normally we know that key this melting point, boiling point, all this depends on van der Waals forces, right? And it increases with increase in overall mass and surface area. So if we talk about use these aryl halides, then since iodine has the largest mass among the whole group, so therefore obviously aryl in among them, iodoarine or iodobenzene has got the highest boiling point. It decreases as we move up the group till fluorine, right? So that is how the the overall property is going to lie over there. One more thing that we have to remember, and it is quite often asked in your paper, if you talk about like chlorobenzene, and if you talk about right chlorocyclohexane, now these two have got quite a large difference in their dipole moments, right? This one has got lower dipole moment while this has got higher dipole moment, right? Why is it so? You can see that, you know, this is of sp3 hybridization. This has got sp3 hybridization, right? This carbon, while this carbon of benzene has got sp2 hybridization. That means your polarity difference is less here while it's high here. Large difference, and here it is lesser difference. So larger the difference in polarity, higher the dipole moment. And also because of partial double bond character, right? Because of the partial double bond character, what is going to happen is this CCl bond is going to be shorter while the other bond is going to be comparatively longer. So they've automatically dipole moment of this, if I say it, this is mu1 and this is mu2 dipole moments, right? So mu1 is automatically larger than mu2. So this is one explanatory question you are quite often asked in paper, right? I hope this is clear. Okay, then let's talk about the preparation part, how it is done, right? So the first method that we are going to talk about is your electrophilic substitution method, or electrophilic aromatic electrophilic substitution method, right? So mainly chlorides and bromides are prepared by this method, right? We do use iron or iron halide, that is for chlorine ferric chloride or ferric bromide, right? Or we can also use the aluminium chloride, aluminium bromide, anhydrous aluminium chloride, and aluminium bromide part. So Lewis acids are generally used for this particular reaction as catalyst, right? So what happens, your these two, you know, we know that key, you know, any alkyl group is ortho para director, so therefore they will combine with the respective halogen, and you are going to get the ortho part and the para part, right? Obviously para is always going to be major while ortho is always going to be minor, right? So I mean, electrophile is generated with this mechanism. The mechanism for this contains, in the first step, your electrophile is generated, right, with the help of the catalyst. In the second step, you have got the electrophile attacking the aromatic ring and it loses its aromaticity. So in the second part, loss of aromaticity takes place, and in the third part it expels the hydrogen so as to regain its aromaticity, and there you get the final product, because right now it has got a hydrogen here, right, a hydrogen on the other side also, right? So these two will be substituted. It looks like as if there is a substitution in the final product, hence the name electrophilic, because electrophile is substituting in an aromatic system. So you have got aromatic electrophilic substitution taking place over here. So in the last part you regain aromaticity. right? Fine. So right, the one that we talked about, they can be easily separated. See, ortho and para isomers, they can be easily separated by due to their large difference in the melting point. The one that we just spoke about, ki the boiling points of these dihalogen or these halobenzenes are not that large. The difference is not that large, but when you talk about the melting point, then it is quite large. Why it is happening? Because you might have studied in solid state that better the geometry of packing, stronger the overall lattice system, and hence it is more difficult to break the arrangement, which automatically increases their stability and hence the energy required to segregate them, separate the atoms or molecules, which means to melt them. So more the symmetry, basically, if we talk in simple algorithm, better symmetry will lead to better packing and hence higher melting point. So you can see that in an para position, the symmetry is quite high, right? It's almost like the arrangement is like this at the molecular level. So they will be setting up something like this. But in case of your ortho, so the geometry is not that conducive to put them, in a close array. They will be a little bit away from each other because there will be hindrance, and hence a small amount of energy will be able to disrupt the order and they can easily melt away, right? So that's the main reason behind this. Okay, the way we are doing the reactions with chlorine and bromine, it's not possible to make iodobenzene also in the similar fashion. Why? Because one iodine reacts slowly and it's a reversible reaction. Hence the output is not going to be that high. So what do we do? Because in the product you're like in the last case, you see that the byproduct is going to be plus HCl or HBr, right? This is going to be your byproduct, and similarly here also the byproduct should be HI. Now the problem is that HI is again going to react with the final product and give you back the reactant. So it's a reversible reaction. So what we can do, if somehow we can remove HI, then as per Le Chatelier principle we will be moving forward because it's an equilibrium, right? So what do? We oxidize HI to I2 with the help of these good oxidizing agents. So when this is oxidized to iodine, obviously chances of going back will be lesser. Fluorine we avoid altogether. Why? Because fluorine is extremely violent in reaction. It's quite explosive. So serious harm can be done. So therefore we avoid fluorine by this method. We do make fluorobenzene also, but by some other method called Bals-Schiemann method, right? That we will discuss later, right? Okay, now from diazonium salt, the other method is with the help of diazonium salts. Diazonium salts are very versatile compounds which we can use to make a lot of different organic compounds, a wide array of organic compounds, right? In the similar fashion like your Grignard reagent. So both Grignard reagent and your diazonium salt, these two are extremely helpful organic compounds with the help of which we can make a lot of different organic compounds. So how is your diazonium salt made? By the way, diazonium, diazo is the Latin for nitrogen, right? And we have got two nitrogens over here, so N2 is here, so diazo, and it's a positive charge, hence em. So therefore the name diazonium, right? And of course it's a salt, right? So what happens ki when you react aniline with nitrous acid, now the problem is, unlike nitric acid, nitrous acid is very unstable. So to prepare nitrous acid separately and store it is a very difficult proposition. So what we do, we use sodium nitrite and HX, whichever acid is needed, like HCl or HBr, in situ, that is during the reaction only, and your nitrous acid is generated, which then reacts with aniline, right, to give us benzene, diazonium, and whatever the halide is, right. But one thing is very important for us to remember: the reaction conditions, right? It must be maintained between 0 and 5 degrees Celsius, which is your 273 to 278 Kelvin. Because if you go beyond 278 Kelvin, then in place of this, we have got aqueous condition. So in place of this, we get phenol. So we have to be very careful. We should be careful about maintaining this temperature range. Otherwise, desired product won't be formed, right? Acha. Now what do? Once this diazonium salt is formed, we react this with your copper salt of the halide, cuprous halide we are reacting with, right? Your Cu2Br2 or Cu2X2, Cl2, cuprous chloride, right? And hence we get this output. So this is called your Sandmeyer's reaction, right? It is called Sandmeyer reaction. Now there is an alternative to this reaction also. In place of this, if you use copper powder and the respective halo acid, then also the same output is obtained, and that is your Gattermann reaction. We will talk about that also here, right? I hope till here everything is clear. Just let me check if I can still find me live, since I'm not finding myself. No, somehow I'm unable to log in, students. Okay, so not sure. Fine. So in the similar fashion, if we react this, now we do not need any cuprous salt of iodine, right? We don't need cuprous iodide. If we even warm it with potassium iodide or sodium iodide for that matter, then also we can prepare by just by shaking, we can have iodobenzene. So see, earlier iodobenzene was reversible in nature if you react it directly with the help of ferric iodide as catalyst or iron as catalyst. So there you had to use your some oxidizing agent, right, to control it. But now you don't have to do that. With diazonium salt, it is very easy to make. You just have to use Ki, which generally we use either dry acetone, dry ether, so as to stabilize the whole thing, and we get iodobenzene in good amount, right? Okay, and of course Kx will be formed here. Along with this, we'll be also having Kx, right? Acha. Now the other method that I was talking about. So if you use copper powder, see, if you use copper powder with the respective halo acid, it can be HCl, HBr. So you can again have chlorobenzene or bromobenzene for that matter. Now this is called Gattermann reaction. Earlier that was Sandmeyer reaction. It is the modified form of Sandmeyer reaction called called Gattermann reaction. Now how do we make fluorobenzene with the help of this? What do you have to do? You react this with HBF4. You react this with HBF4. right? Now hydroborofluoride. So what happens? HCl is removed, BF4 attaches itself with the diazonium, right? So you have got this thing. So when you heat it, your N2 will go away from here, BF3 will also go away from here, fluorine is left and it will attach itself with the benzene. Now because this one of the fluorine is bonded with BF3 as a coordinate bond, so it will shift over there and we get fluorobenzene. It's quite safe, it's not dangerous to obtain fluorobenzene like this, unlike the previous methods. So mostly we use this method only to get our share of fluorobenzene, right? Okay, now another method. Generally phenol does not react with PCl3 or HX like that directly to give you the nucleophilic substitution reaction. However, if you react with PCl5 and that to with warming, with a little bit of heating, like around 70-80 degrees Celsius, it reacts with this. It is then capable of breaking this bond, and then one chlorine shifts over there and you get chlorobenzene like that, right? So this reaction is also important to obtain your chlorobenzene, right? PBr3 is highly unstable, so we cannot have like bromobenzene like this. So this reaction is better for chloro component only, right? Okay, now a question for all of you, right? So if you have got this toluene with bromine and the catalyst ferric bromide, what is the major product of A? Remember, major product of A, right? So I'll give you all 30 seconds to think about and then give me the answer. So I believe all of you must have arrived at the same conclusion, that is C is the right answer. Why? Because after reaction with this, you are going to get only the ortho and para components. That's what we learn, right? This and this one. And we know that whatever you do, para is always the major one, right? Since they have asked you the major product, so the only one option is correct, that is C, right? Okay, right answer. Now what types of reactions do we see? So after preparation of haloarenes, now the next part is your their chemical reaction. So what type of chemical reactions do we see for aryl halides? So we see nucleophilic substitution, right? Normally nucleophilic substitution reaction is not conducive for your aryl halides, but under certain conditions we can still make that happen, right? Majority what they do is electrophilic substitution reactions, and there are certain reactions with metals also, the way we had for your alkyl halides. Remember, like Wood's reaction we had, right? So similar reactions are possible for their aromatic counterpart also. Let's explore them one by one. Okay, now unlike as we were just discussing, unlike alkyl halides, aryl halides cannot easily undergo nucleophilic substitution reactions. They cannot undergo nucleophilic substitution reactions, right? Why does this happen? So if you think about the resonating form, you will arrive at few conclusions why it is not happening. Let's explore them one by one. In any case, whenever you have got a halobenzene, right? Whenever you have got a halobenzene, then you can easily see that there is this plus R effect that is taking place, right? This plus R effect is taking place, which means you will always get a partial double bond. You will always get a partial double bond over here, right? So it is easier to break a single bond than a partial double bond. So therefore, any incoming nucleophile will always find it difficult to break this in comparison to the one with the alkyl halide, right? Acha. And also because of this partial double bond character, in fact, benzene, all the carbons in benzene are what? They are all sp2 hybridized, right? So you can see that key carbon with sp2 hybridization in case of aromatic halides and sp3 hybridization in case of your aliphatic halides, the difference is quite large. Difference is quite large. Here the difference is smaller. Of what? Electronegativity, right? So therefore this bond is less polar, and here the difference is large. Electronegativity difference is large, and hence this bond is more polar. So you can see that aliphatic carbon halogen bond is more polar than aromatic carbon halogen bond. So therefore you can say tearing them apart, or ionization of the so-called aliphatic carbon and halogen is easier than that of the aromatic one, right? So therefore hybridization definitely becomes a factor. Okay, now think for a moment कि somehow you have removed the halogen, then what is left behind? What we get once you remove this is a phenyl carbocation. Now a phenyl carbocation is much less stable than any aliphatic carbocations, whether it is primary, secondary or tertiary. This is much less stable. Just think about a vinyl carbocation. A vinyl carbocation is much less stable than even your methyl carbocations, right? So therefore this is not going to help our cause, right? So not suitable, obviously, right? Acha. And also your benzene ring is heavily, it has got high electron density. So a nucleophile which itself is also negative, so both these negative systems are going to kind of repel each other. Both of them are going to give each other the cold shoulder. So what is going to happen? Nucleophiles will try to avoid such kind of a system where they receive no warmth, है? So they will avoid this type of aromatic system. So what happens? All these factors tell us that somehow nucleophilic substitution reactions are not welcome for aromatic system the way they are in aliphatic system. So we see easy nucleophilic substitutions in aliphatic systems that we studied about in our previous classes, but in case of aromatic systems, until unless you create a special environment or that aggressive reactant is not there, this thing does not take place, right? Okay, so the resonance effect that we were talking about, so you can see that in all these three structures, what do we have? We have a partial double bond character until unless it comes back, right? You have got this, it will come back, it will go over there. So you are going to get the shifted original structure, right? This one. So you have got back your aromatic character, that's fine. But these three important structures, they show the partial double bond character, right? And hence it's difficult to break them, right? So hybridization, as we discussed, it's sp2 and this is sp3. Obviously your polarity will matter, the difference is going to matter, right? X is going to be same, so it has got its fixed electronegativity. But for carbon, sp2 is more electronegative than sp3. We all know that more the s character in hybridization, more the electronegativity, right? Which clearly shows that CsP2 is more electronegative than CsP3, and hence of course that lesser difference in polarity, right? Okay, then what do we have? As we discussed, phenyl cation is not at all stable. A phenyl carbocation is not at all stable. It is even less stable than aliphatic alkyl groups. Got it? So therefore it is not conducive in the mechanism also to go through phenyl carbocations. As we discussed, both have got high electron density, right? If you talk about a benzene ring, whichever group it has got doesn't matter, and then you have got a nucleophile, simply they don't gel well with each other, so there will be kind of repulsion among them, right, because of similar charges, right? Okay, fine. So now you can see that if we have to do nucleophilic substitution reaction, it has to be little bit of spatial condition, more aggressive condition, corrosive condition, vigorous condition, right? So what we are doing, we are trying to have replace chlorine and get OH over here. So from chlorobenzene we are forming your phenol, right? But to do that, what we have to do? First we have to use sodium hydroxide at 350 degrees Celsius and 300 atmosphere. So what do you get in between? You get sodium phenoxide, right? And from there, when you do hydrolysis, you get your phenol, right? Acha. Now this is also called your Dawes process. So you have to use this aggressive condition. You cannot do this at room temperature, right? So under normal conditions, again this would have been a no reaction, but with this it can happen, right? Okay, now if you start putting what electron withdrawing groups, see what we have here earlier is, here there is no electron withdrawing group, but if you put here electron withdrawing groups, what happens then? This electron density is drained out. Electron density of the benzene ring is drained out, and then removal of chlorine by another, replacement or substitution of chlorine by another nucleophile becomes quite easier, right? So you can see right now we are using 623 Kelvin and 300 atmosphere. Now you put one nitro group over there, which is a very strong deactivating group. You can see that there is no extra pressure, right? And also the temperature from 623 Kelvin has been reduced by 180 Kelvin to 443 Kelvin, right? And now the reaction is much easier. So we are using less vigorous condition if we are able to use some electron withdrawing group, and nitro is a very strong electron withdrawing group. So see, if we are putting one nitro group, we are seeing this type of change. If you use two nitro groups, two strong electron withdrawing groups, then the condition should be further smooth, right? It should be smoother than this. And if you use 3 nitro groups, then this substitution can take place at close to ordinary conditions, right? By just simple warming also this can take place, right? But they have to be used on ortho and para positions only. Meta position is not going to help. Why? Because during resonance the electron shiftings are taking place only at the ortho positions and para positions, but not at the meta position, right? So let's see, if you have got two, see the condition has become further smoother. From 423 you have come down, 443 you have come down to 368, right, with two of them. And if you have got 3, then all you need to do is simply warm it, right, close to your normal conditions. So therefore, more the electron withdrawing groups at ortho and para positions, easier it is to do nucleophilic substitution reaction, right? Okay, so why we were discussing that? See here, when it is present at the para position, I mean this can also be part of the resonance. So basically you are drawing out the this electron ring density towards yourself, which means your replacement of the OH group or the addition of the OH group to this particular carbon becomes more easy, or it becomes easier by easier to put it over there when nitro is there in comparison to when nitro group is not there, right? See, this whole electron density is now pulled towards the nitro group, right? Okay, now if it is at ortho position, then also the similar effect is seen, right? It is still easier to remove it at para position or nitro position. You can see how the electron transitions are taking place, right, in terms of resonance. So the same thing. But if it is at meta position, then it is very difficult. And because electron electron distribution is kind of forced one, and nitro is not at all helping. Hence we see there is no effect if you put the nitro group at the meta position. That's what we discussed few moments back also, that all these effects can be seen only if the electron withdrawing group is present at ortho and para position. If it is present at the meta position, since it is not being part of the electron distribution arrangement, it does not impact the removal or substitution of the chlorine, and hence this step is futile, right? So the first step controls everything. Fine. Okay, now let's move on. These halogen, now we are moving on to the electrophilic substitution reactions. It's a very interesting case. What happens? These halobenzenes, they do so plus R effect, all right. Right. So if I remove the circle, let me use this. So we do see a plus R effect, but at the same time, this being an electronegative atom, it also pulls electron density towards it with the help of the sigma bonds, which means minus I effect. So minus I effect and plus R effect are in opposite directions. They are going to not make it very easy for the whole system to undergo your electrophilic substitution reactions, right? So what happens? Plus R effect will make them make the electrophiles get added at ortho and para position. That's all right, but then minus I effect weakens that. So therefore halogen atoms are ortho para directing, but they are the weakest weakest groups to undergo ortho para substitutions, right? So therefore they are slightly deactivating, while others are activating. Ortho para your halogens are deactivating ortho para directing groups. They are also very weak ortho para directing groups, right? Let's explore further. So this is the plus R effect resonance that is taking place over here. So it is you can see that, you know, lone pair is coming here, that is moving further. This is wrong, this should not have been there. Don't consider this, please. Right, and then this whole electron keeps on moving further, and in the last case again, what is going to happen? This will come over here, this will go back, we will obtain the aromatic ring back with all the bonds shifted by one place, right? And the partial double bond character will be removed, and this cycle will keep on happening. You can call it the fifth structure. Fine. Okay, now, so as we discussed, because of this resonance electron distribution, electron density at the ortho and para position is pretty high, but because of the minus effect, as we discussed, it will be little bit of weak nature, right? Okay, so what happens? The substitutions are supposed to happen at ortho and para only. So if you do halogenation, see, you are having it at the para and ortho position, and as we discussed, para position is always major, right? So halogenation or nitration for that matter is again the same thing. See, your para position is major and ortho position is minor. Sulfonation, again ortho position is minor, para position is major. So what are the electrophiles here? In case of halogen, it is here it is, since chlorination is happening, so it is the Cl plus, that is your electrophile, right? In case of nitration, you have got again Na2 plus as the electrophile with H2SO4 as the catalyst. In case of sulfonation, obviously you remove OH and you have got, so this is also acting like the auto catalyst, right? So SO3H with a positive charge here, right? And even in some cases you can the mechanism is with SO2 also, and here the carbocation formation is going to be your, so methyl carbocation is our electrophile over here, right? So Friedel-Crafts alkylation, acylation, sorry, this was alkylation, and in acylation this is the acyl group, so you are again going to have C double bond O CH3. This is the electrophile that is going to attack. So it's a very good method to prepare your aromatic your aromatic ketones over, like this. So in the chapter of ketones, this is the same reaction you are going to use for your preparation of aromatic ketones, right? Okay, now the third segment. What is the third segment? Just like your Woods reaction, we can have Woods Fittig reaction. Actually, your Fittig reaction is when we will discuss that also. Fittig reaction is when your two different aromatic molecules, aromatic molecules, they come in they interact with each other with sodium present in dry ether, right? So sodium will extract the X, and two aromatic rings will, the two phenyl rings will combine with each other. That is your Fittig reaction. So when you have got this halo aromatic group with Rx, so what happens? They will interact with each other and they will form this combined compound. But since sodium is there, then these molecules are also going to react and form RR, right? That is your Woods reaction will also take place, and these two will combine to form, to give you Woods Fittig reaction. So basically, as a byproduct, you also get the Woods product. Got it? Okay. So I was talking about Fittig reactions. In case of Fittig reaction, what is happening? Again, sodium is doing the same thing, and these two phenyl groups are attaching with each other, and thus we are getting biphenyl. So this compound is biphenyl. Right? Exactly in the similar fashion. Now there is Ullmann reaction also. right? So just like your phytic reaction, in phytic reaction you use sodium with dry ether. So in place of that, if you use copper powder, then that is called your Ullmann reaction, and that happens with iodobenzene. So again, copper will remove iodine and you will get biphenyl like this. So to prepare biphenyl, you can use phytic reaction as well as your Ullmann reaction, right? Now let's discuss this question quickly. So which of the following compound undergoes nucleophilic substitution reaction? Just be careful, nucleophilic substitution reaction they are asking for, right? And this happened with electron withdrawing groups, not donating groups. So your this methoxy group is electron donating group, so this is not going to happen. It never happened easily with halobenzene stuff. It is also electron donating group. So what we are left with is the third third option, because it has got electron withdrawing group at para position. So that's your answer, right? Okay, next one. So you have got chlorobenzene with copper cyanide. So what is going to happen at high temperature? See, this is pretty high temperature. So Cn is going to replace Cl, and you are going to have here Cn, right? Now they are doing hydrolysis. So when you do hydrolysis of this complete, in case of complete hydrolysis, you are going to have a carboxylic acid, yani benzoic acid is going to be formed. Now if you use this mixture, sodium hydroxide with calcium oxide, this is called soda lime. Like the soda lime is used for step down reaction. So presence of sodium hydroxide will remove this hydrogen and make this the sodium salt, that is sodium benzoate. So when you use soda lime over here, as I told you, this is step down reaction. So what is going to happen? In case of soda lime, what is going to happen? Carbon dioxide will be removed, sodium carbonate will be formed, and you will get a hydrogen over here. So therefore you should get C here, right? You can see that no amide is formed. A will be not A, this will be benzoic acid, so B is not there, and even this is not there. So let's see. So this is your answer. I hope you have been able to, all of you have been able to follow the logic behind these A to B word problems actually. Okay, quite interesting one. So you have got benzyl alcohol, right? It's a benzyl alcohol. So when you are dealing with such a compound with SOCl2, thionyl chloride, so what is going to happen? It's a chlorinating agent, a very strong and good chlorinating agent. So it is going to replace this. So in A, you are going to have benzyl chloride. So you are going to have benzyl chloride. Now when you are reacting this with KCN, obviously just the way it happened in the previous example, there of course your high temperature was needed because that was an aromatic substitution. Now it is aliphatic substitution. So Cl will be replaced by Cn. So what you get is Cn. Now when you hydrolyze this, we already discussed that in the previous question, you should have this as the carboxylic group, right? So that means your C will be third option, right? So this should be the answer. Here it is. You get this as the final answer. Let's see now. Okay, so what do we have? So you have been given chlorobenzene and you are doing nitration, right? So when you are doing nitration, you are going to have A over here as nitrobenzene, right? Where as you take the major product, that is at the para position, right? We are taking the major product here. So chlorine is here, ortho and para nitration will take place. Let us take the major one. Nitro is there. Now you are doing Dawes process. But see, since there is an electron withdrawing group, extra pressure is not needed. So substitution should take place, right? Cl should be replaced by OH. And which option shows you that? So it cannot have two OH groups. Ortho we are not considering, and also B cannot be this one because this will be replaced. Two nitro groups is not there, so we have got the fourth option as the final answer, right? So thanks all of you. We come to the end of the class, and I hope we all have learned a lot about aryl halides. Any further doubts, please do ask me. I could not check myself live, so maybe in the next class, if you have got any doubts, please do ask me. I'll be more than happy to answer all your doubts. So this is goodbye from your chemistry mentor, Rahul sir, Ghosh sir. We'll see in the next class with new topic. Take care. Bye. And thanks for joining.